which case we get Z1 dot equals Z2. Z2 dot equals 1 over M2 K D1 minus D2 minus B over M2. I'm just going to write that in terms of Z's. I get 1 over M2 K Y minus Z1. Sorry, I'm missing it. All right. Minus B of Z2 over M2. We know Y double dot, so let's keep differentiating. Z2 double dot is equal to K over M2 Y dot minus Z1 dot minus 1 over M2 d by dt of B of Z2. And Z1 dot is just Z2. So Z2 triple dot, I guess you really shouldn't write triple dot. Z2 differentiated 3 times is K over M2 minus K1Y minus K2Y dot minus 1 over M2 K Y minus Z1 minus 1 over M or B over M minus 1 over M2 d by dt squared of B of Z2. I'm missing a bracket here somewhere. I'm missing a bracket here. There we go. That should fix things up, right? So I'm a little bit stuck here because I used this nonlinear friction. So nonlinear friction, it's a little hard to see whether that's a stable system or a non-stable system. So for the sake of analyzing stability, I'm just going to approximate friction with a linear term. It's not too unrealistic. Because friction is approximately linear anyway. I know you know, there's nonlinearities in the friction, but I know they're going to be, you know, it's very unlikely that nonlinearities in the friction are going to make me go unstable unless they actually turn into positive friction or something, right? So I'm pretty safe just approximating one nonlinear friction with a linear friction term to analyze stability. So let's say B of Z2 is approximately equal to some friction coefficient times Z2 in some area of approximation. And then I get Z2 cubed, not cubed, sorry, differentiated 3 times. I just get some constant A1 times Z2. I'm not going to write all these constants out. You get the idea. So A1, A2, A3, C1, C2, and D are all positive constants. I can work them out if I need to, but it's going to be enough for me to know that they're positive constants. So what I get is Z2 dot, Z2 double dot, Z2 differentiated 3 times is equal to 0, 1, 0, 0, 0, 1, A1, A2, A3 times Z2, Z2 dot, Z2 double dot, plus 0, 0, 0, 0, 1, 1 times Y dot. Y dot. Okay. So the way I look at this in terms of stability, I say zeta dot equals A zeta plus B gamma, and this is the input here, and I have the real part of the eigenvalues, or I should say, if the real part of the eigenvalues of A are less than 0, then the system is stable. The zero dynamics are stable. So I don't have to worry about the input, because the input comes from the other system, and I've already proved that the other system is nice and stable. So mass 1 is already nice and stable, I know that. So this input's coming from mass 1. So I don't have to worry about the effects of this input. This input isn't going to make the system go unstable. So I can just ignore it for stability purposes and just look at the actual dynamics of mass 2 here. So feedback linearization, the control design, is usually pretty straightforward, as you can see. It's analyzing the zero dynamics that is the tricky part, right, for feedback linearization. But the actual control design is pretty straightforward. So any questions on feedback linearization? So I could have done the same technique, same feedback linearization technique for controlling mass 2, but in that case I wouldn't have got zero dynamics, because both masses would have ended up in my equations if I had looked at mass 2. So the zero dynamics only occurs because I'm controlling mass 1, and the control input is mass 1. So that control system doesn't deal with mass 2 at all, so I do have to analyze the dynamics of mass 2. So like I said, I didn't use feedback linearization for controlling mass 2 because I know that it's hard to make adaptive, so I'm not going to bother teaching it. Although there's lots of papers in the literature that like it, but basically to use feedback linearization for mass 2, you basically have to know the model. And if you did try to make it adaptive, it'd be very, very difficult. So that being said, now I want to do adaptive backstepping. So let's see how we can make backstepping adaptive. So I should make a note, you can still get into analyzing the zero dynamics for something like a robot, because even if you're doing a flexible joint robot and use backstepping, your links might be flexible. Maybe you didn't take that link flexibility into account. Something like the Canadarm on the space shuttle has really flexible links as well. So maybe you do a control for the flexible joint part of the robot, and the flexible links you don't have specifically in your controller, so the flexible links could end up in this kind of zero dynamics analysis. So you could still end up with kind of analyzing zero dynamics even with backstepping. There are certain dynamic part components you were ignoring in your control system. So just keep that in mind. Well, let's do adaptive backstepping. Two ways to do it. I'm going to teach you the over-parameterized design, which means we're going to end up using a new neural network at each step. So let's just teach it to you with a simple system and then do it for the flexible joint robot. Because flexible joint robot equations are a little complicated and might kind of disguise the basic methods. So here, W1 tilde is either a parameter error vector in an adaptive control, or B, a weight error vector in a neural network control. The math will be the same in either case. So V1 dot is equal to x1 f of x1 over g plus x2 minus 1 over beta W1 transpose W1 hat dot. And I'm going to define Z equal to x2 minus alpha. Where alpha is a virtual control. In other words, a desired value for x2. So to assume we have f of x1 over g being equal to gamma 1 of x1 times w1 plus d1 of x and t. Gamma 1 is either nonlinear functions, adaptive control, or basis functions in neural network control. And d1 of x and t, should be x1 there, includes modeling errors of the neural network, and actually I'm going to take the t out. So I was going to put external disturbances in here, but it's actually probably not the right place to put them, so I'll just leave them out for now. And just point out that we can throw them in if we want to. So we have v1 dot is equal to x1 gamma 1 of x1 times w1 plus d1 of x1 plus z plus alpha minus 1 over beta w1 tilde transpose w1 hat dot. Since my definition for w tilde was the ideal weights in the neural network, or the correct parameters minus my estimates. The correct weight vector, or the correct parameters, are constant, so the derivative would be 0 if you remember from last lecture. So I could choose alpha equals minus gamma 1 of x1, w1 hat minus k1 x1. And I get v1 dot is equal to x1, gamma 1 x1, w1 tilde plus d1 of x plus z minus k1 x1 minus 1 over beta w1 tilde w1 hat dot. So v1 dot is equal to minus k1 x1 squared plus x1 d1 of x1 plus x1 z plus w1 tilde transpose gamma 1 transpose of x1 times x1 minus w1 hat dot divided by beta. And choose my robust weight update. If you remember, I can't just choose this to make this term equal to 0. It's tempting. It looks like I can just make this term equal to 0 and all the bad stuff disappears. But remember, because the d1 of x1 there is there, if I do that, the weights will go up to infinity and eventually cause bursting in my system. So I want to make sure the weights don't go up to infinity, so I need to make a robust weight update. So last time we learned about E modification. And leakage. Yeah, we learned about E modification and leakage, sorry. E modification was the one where I had the magnitude of the error in there. And leakage was the simpler one where I just had nu times the weight. So I'll just use the simpler one here. So V2 dot equals x1 d1 of x1 plus z d2. No, that's not right. Where are we? Sorry, I was getting ahead of myself. It should be ones here. And this should be x1. Yeah, there we go. Much better. Sorry about that. I was looking ahead to step 2. So in step 2, I get V2 equals V1 plus 1/2 Z squared plus 1 over beta W2 tilde transpose W2. So you can see that I'm introducing another neural network at this point, or another set of adaptive parameters, W2. So I said at the beginning this was the over-parameterized design. So it's actually possible to do this with only one set of adaptive parameters. So I could just have W1 tilde and not introduce any other neural networks or adaptive parameters. But it gets complicated if I do that. It does work a bit better, but it's very complicated. So I'll just stick with the simpler method, which is the over-parameterized design. So the purpose of this will really be a differentiator. So remember we were in the previous method of backstepping, I had an alpha-1 dot, and I said alpha-1 dot had to be calculated by analytic differentiation. Well, you can kind of do the same thing here if you really want to have an analytic derivative of this, but that's a real pain. So it's easier just to have a neural network that estimates alpha-1 dot. So you're basically using the neural network as a differentiator, essentially, to learn the derivative. Okay? So that's what we're going to be doing. So let's see how this works. V2 dot is equal to V1 dot plus Z, x2 dot minus alpha dot minus 1 over beta W2 tilde transpose W2 hat dot. So we use second neural network or set of adaptive parameters. To estimate the derivative, minus alpha-1 dot is equal to gamma-2 of x W2 plus D2 of x. Okay, so note, I think I forgot to write this the first time, but note that we must choose the neural network large enough such that I can bound D2 of x. So D2 of x is a modeling error, and it'll have to be D less than or equal to D2 max for all x in some region of approximation. I should have written the same thing when I did D1. I just forgot that line. But the modeling error of the neural network always has to be bounded, essentially, for this to work. So now I'm basically using this neural network as a differentiator. So I get x1 times d1 of x1 plus x1z minus k1 x1 squared plus nu w1 tilde transpose w1 hat plus z u plus gamma 2 of x w2 plus d2 of x w2 transpose minus w2 hat dot over beta. So now I can choose my control. U equals minus gamma 2 of x w2 hat minus k2z minus x1. And I can design my weight update w hat dot for w2 is beta gamma 2 transpose of x times z minus nu w2 hat. So v2 dot is equal to x1 d1 of x plus z d2 of x minus k1 x1 squared minus k2 x2 squared plus nu w1 tilde transpose w1 tilde plus nu w1 w1 hat, this should be w2 tilde times w2 hat. So we have an analyzed stability is let call x bar equal to x vector xz, d bar equals d1, d2. With the norm of d bar being less than or equal to d max. I'll call k bar, I'll call this k1, k2 on the diagonal. And w bar, I'll put the w1 vector and the w2 vector together. And then I get v2 dot is equal to minus x bar transpose k bar x transpose d bar plus nu plus nu w tilde w minus nu w tilde transpose w tilde. So v2 dot is less or equal to minus minimum eigenvalue of k bar times the norm of x bar plus d max times the norm of x bar plus nu times the norm of w tilde times the norm of w minus nu times the norm of w tilde squared. So v dot is less than 0 if either x or w tilde gets large enough. Therefore, all signals are uniformly ultimately bounded. And just like when we did E-modification, I can calculate those bounds. So I can calculate what the uniform ultimate bound is easily enough. So now I can make my backstepping method adaptive. And I can use neural networks instead of adaptive parameters if I want to make things even easier. The neural networks just make life a lot easier. Using the adaptive parameters is kind of a pain. Especially when you go through multiple steps of backstepping. Because at each step of backstepping, the neural network is the same complexity, but the amount of adaptive parameters you would need would go up kind of exponentially as you go through steps of backstepping. So the adaptive design gets very complicated if you're not using neural networks. So neural networks are basically advantageous for their simplicity when it comes to the backstepping design. So I'll do this now over again. So now we know how to do backstepping, we know how to do adaptive backstepping, so now I'll show you how to do adaptive control of the flexible giant robot. So it's basically the same stuff I just put up on the board, just with more details and the actual robot dynamics in there. I mean, there's a few tricky little details that you have to kind of like bookkeeping details basically when you're doing backstepping. Nothing conceptually different than what we just learned. So let's take a 10-minute break, come back at 20 after 3, and I'll just finish off with the adaptive backstepping for the flexible giant robot. Okay?